Calculate from 40 carbon H to B delta 14 carbon value per mole for the following surface ocean. Hint: F is the same in equation 3.10, 3.16, 3.16, and 3.18. And assuming y equal to 2022, A 300 years in the Middle Ocean Geos, and then 70 years in the Eastern Tropic, 1,040 years in the Southern Ocean. First, utilize the information provided in the problem statement to substitute values into the formula 4.60 to determine F. Then calculate the expression F times expression 1950 minus Y divide 80 to 67 equal to F prime minus 1 times 1000 to obtain the final answer. And my final answer is following.
Can you tell us where is the C14H that you need to put into? Using this equation, you can convert C14H to what?
To F.
To F, right. What is needed to calculate from F to big delta?
这个 B delta 14的值是等于 F 逗点，这个等式又可以等于 F 乘以 expression 的这一项式子，最后我把它代换，就会留下 F。
That means you calculate from equation 3.18 to F plum, and then from F plum you use 3.17 to big delta C14. Good. I need to check the number, but the logic behind the calculation is correct.
Please draw a counter line on figure 5.2 to indicate the bound 14 carbon signal in the Western Atlantic Ocean. Where does the bound 14 carbon penetrate deeper in the South or North Ocean? What will be the reason to explain this uneven distribution? According to the figure 5.1, we can identify the bound 40 carbon signal in the red counterline of the figure 5.2. This one. 40 carbon penetrate deep in the North Atlantic compared to the South Atlantic in the 1960s. Nuclear weapon tests leading to the sharp increase in B delta 40 carbon dioxide in the northern hemisphere. The North Atlantic warm currents, when reaching high latitude, undergoes cooling and sinking, forming the global thermochemical circulation (THC). Simultaneously, it transports substances such as 40 carbon to the deep sea. The reason for the uneven distribution of 40 carbon in the South and Northwest Atlantic is attributed to the fact that this chart was created in 1980s, a time when the high 40 carbon content THC had not fully traversed the Southwest Atlantic, causing regional differences. What is the difference between the B delta 40 carbon of DIC and the B delta 40 carbon of DOC at 0 meter in the North Atlantic Ocean? What is the corresponding difference is 40 carbon H? DOC 的 C14的值是负250千分比 ，DIC 的它值是80千分比。之后再根据我前面的逻辑计算，会得到这两个数值。DOC 的话算出来是223。
Good. This is a well-known phenomenon for marine chemistry that dissolved inorganic carbon is much younger than dissolved organic carbon of the same water depths. And the difference is up to a few thousand years. There are many explanations for this.
The first question is we have to calculate the 14 carbon H from the delta 14 carbon value. We have to calculate the three ocean, and A is northern North Atlantic, delta 14 carbon value is minus 70 per mil, and B is the deep Atlantic, and the value is minus 160 per mil. And Indian is minus 190 per mil. C is North Pacific, and the value is minus 214 per mil. And the equation I use is these two and this. We can see the delta 14 carbon is like this. And the F prime is here. And this F prime is equal to F times the exponential here. Also, in the material, it tells us that F prime is equal to the delta 14 carbon divide 1000 plus 1. We know F prime is equal to the F times exponential and this. So we can know this equal to this. So we can know F is equal to here. And also, it tells us that 14 carbon H is equal to minus 8033 long F. So we can know this. I make a sheet, and the question we have to answer is for location. And the F is like this. You can just use this and you put in the formula and you can get a number. We know the F. 14 carbon H is minus 8033 long F here. You can get the 14 carbon H. The Y in the equation is the sample you measured because teacher didn't say. Now it's 2023, so I just put the 2023 in this Y. The next question is, what are the two carbon source pools for the DIC in surface ocean? And which one takes longer to exchange carbon with the DIC? The source pool for the DIC in surface ocean is atmosphere and the deeper ocean. Atmospheres takes longer time to exchange carbon with the DIC because the rate of the CO2 exchange, the value is not very big, like here. It will probably take 10 years for the DIC in the surface ocean to exchange with CO2 in the atmosphere. But the exchange of the surface water by mixing will take fewer than 1 year. That's why the surface DIC is much older because it mixes with the deeper and older water. Question 3 is we have to mark the location of the youngest and the oldest bottom seawater on the figure 5.3. And what are the 14 carbon H respectively? And question 1, we just calculate the 14 carbon H from its delta 14 carbon value. So we can just calculate this minus 15 to minus 225. I make a sheet. The delta 14 carbon value minus 50 per mil, its 14 carbon H is 482, and the minus 225 per mil, its 14 carbon H is 2118. So we can know when the delta 14 carbon value higher, the age of it is younger. The red side is the youngest. In the graphic is here. And the purple side is the oldest. It's here.
The logic behind the calculation was all correct, and the presentation was also clear. And I also appreciate this kind of tabulation. It will be easier for you to know you are at which step, because if you write a very long equation, it's easy to get lost at some step and then you might make mistake. This kind of tabulation is very much encouraged. I will continue with radiocarbon dating today. This is probably one of the most often used technique in this department because it can be used not only for dating, but also for answering some scientific question that is not related to dating. So it's a very useful technique. This technique was established by Libby. He was a scientist of last century, but he was not the person who discovered that cosmic rays can generate neutrons, which then interact with nitrogen of N2 to produce C14. This person was the person to discover this, but Libby's contribution was he realized that how C14 can be used to date carbon-containing material. And that was 7 years after the discovery of C14. He was awarded the Nobel Prize for this work. Cosmogenic C14. Cosmic ray, it is still present today. It has acted for many, many years. That's the reason we can assume that the C14 flux today is the same as maybe 1,000 or a few thousand or even 5,000 years ago. C14 is produced continually in the atmosphere. So the assumption is the ratio C14 to C12 observed in Earth's atmosphere has stayed constant through time, like today, which provide a universal starting point. If you recall the radioactive decay equation, the A0 for C14 is assumed to be the same as today. Decay equation, how A0 defined? Like today. Practically, it's not like you go out and take a bag of CO2 and use it as your A0. It would be too much complicated. When scientists want to measure C14, they need to use a standard that can be more easily distributed. What they use is this, OX1. In short, OX1. What is that? OX1 is this, oxalic acid. It is an organic compound. It is extracted from sugar beets. Because this sugar beet was produced like a modern product, it should record the signal of C14 from the atmosphere. The activity of modern is defined as the activity of OX1 times 95%. I will not go into the detail of 95% here because that would be too complicated for you. You only need to know the A0 is from this standard. Here you need to pay attention. When we talk about modern in C14, it means present, it means 0 C14 year, it means not today, but 1950. It doesn't mean the year of measurement. Now, I need to talk about some complications. The so-called mass-dependent fractionation. Even most of you do not have any experience with isotope, you probably have heard that life or organisms, they prefer light isotope over heavy isotope. All biological pathways have the tendency for the lightest isotope to be preferentially taken up. This is called fractionation. For example, today you can measure the air. Where we have CO2, you can measure the C14 of the CO2, and you can also measure the tree outside. You can measure the C14 of the leaf. However, even if they are all sampled today, and when you measure its C14 to C12 ratio, you will have less C14 in the leaf than in the air, CO2. This is because life will preferentially take up C12 and therefore make this ratio lower than the air CO2. This will cause bias in dating. Scientists have figured out how to correct for this. Organism fractionate C14 double to that of C13 because of the mass difference. The atomic mass of C12 is 12. Atomic mass of C14 is 14. So the value here is 2. The atomic mass of C13 is 13. So the mass difference here is 1. The mass difference here is twice the mass difference here. If the organism, they have to choose from C12, C13, C14, they will like C12 best. For C13, they will dislike it, let's say maybe a score of 10. But for C14, organisms will dislike them double to that of C13. That's the so-called mass-dependent fractionation. That's the reason why scientists can use C13 for the correction. Stable carbon isotope will always be measured together with C14 for the correction purpose. This is the definition of the delta notation. Delta C13 is equal to the ratio C13 to C12 in the sample divided by the ratio in the standard minus 1 times 1,000. The reason for this 1,000 is because the value here is usually very, very small. For example, without times 1000, the value here would be many zero in the decimal places. And this will make it very difficult to read. That's the reason scientists decided that we need to times 1000 and present with per mil. The standard is PD belemnite, which is a carbonate fossil. And belemnite is like this. It's a little bit like squid, but it has an external skeleton, which is the material we use as our standard. Normalization, a lot of mathematics. This is for students very interested in C14. You only need to know that when scientists want to correct for mass-dependent fractionation, first they measure C13, and then they said we need to normalize everything to the C13 value of minus 25 per mil. You may ask me why. There's no why. It's an artificial definition. Some sample may have minus 20, some sample may have minus 30. We say let's all normalize to minus 25. But for OX1, it's normalized to minus 19. This is the equation for the normalization, but you don't need to know that. You have seen this equation. In your assignment, you have used F. The name for F is fraction modern. If F is 0, it means there's no C14. If F is 1, it means it's modern. When you send your sample to measure C14, this is the value the lab will offer you. They will report F value. F is the ratio of RSN versus RON. R means the ratio of C14 to C12. For mass spectrometric analysis, it's more precise to measure ratio than single isotope. So you see, it's always ratio. So this is the ratio of the sample, and it has been corrected by stable carbon isotope, normalized to minus 25 per mil. And RON, O means OX1, which is our modern A0, and normalized to the delta C13 value of minus 19 times 0.95, which is here. So what you see is actually this one. F is this one. Then we talk about conventional C14H. That's something you need to be very careful. When we say it is conventional, it doesn't mean it is accurate. Why is that? This is a radioactivity equation. I just told you that F is the term here. Then you can use the equation here to calculate the H. And you know from your assignment, C14H can be calculated from minus mean life times natural log F. Okay, it is not half-life, it is mean life. The thing is, the mean life we use is 8,033 years instead of 8,267 years, because this value was reported by Libby, who made substantial contribution to radiocarbon chemistry. This value was a revised value after many, many years of C14 application. Between Libby's mean life and the best estimate, several decades have passed. And during these decades, many, many papers have been published. In order for later scientists to be able to compare their results with earlier literature, scientists agree that even though we know today this mean life is incorrect, we still use it. This is a way how scientists memorize the great contribution by Libby by using his wrong number. Yes, so this one is used in literature. This chart provides a good roadmap for you to link all the mathematics that I have mentioned together. When you send your sample to the laboratory, which is called AMS lab, so this means accelerator mass spectrometry. It's a very special kind of mass spectrometer, and it's very large. It is probably as large as this classroom. So in Taiwan, there is an AMS at National Taiwan University at the Department of Geoscience. The AMS will generate the ratio, C14 to C12 ratio of your standard and your sample. Then you need to send your sample to a separate instrument called IRMS. The full name is Isotope Ratio Mass Spectrometer. This instrument is much smaller. It is probably as big as one of the table here. And in this department, we have such instruments in my lab. You can measure the delta C13 value from the sent sample. So you need two instruments. Having this value, you can use it to do the mass-dependent fractionation correction. With this correction, your ratio will have this subscript Sn minus 25. That means you normalize the value to delta C13 at minus 25 per mil. And O means OX1. So you normalize the ratio to the delta C13 value minus 19 per mil. You have the normalized value. Then you can calculate F, because F is the ratio of your normalized sample over your normalized standard, and the standard has to times 0.95. This is the value the AMS lab will report to you. Lastly, you use Libby's mean life to calculate the conventional C14H. That's the data processing procedure. This is useful dating. For example, when you want to compare with literature, you might want to use conventional C14 data. However, for other applications, you might want to calculate something else. As mentioned in literature, you will see from time to time big delta C14. Big delta C14 reports C14 to C12 ratio of a sample relative to a standard that is corrected for decay since 1950. In the previous equation, you just measure the standard and then you use the measured value. However, the standard will also decay because it was generated or produced last century. When you report this value, you will consider its decay over time. This is again the general decay equation. Activity at T is equal to the initial activity times exponential minus lambda T. You can convert the decay constant to mean life, which is tau here. The big delta C14 has this definition. This looks very similar to here. This is ratio of sample, ratio of standard. Again, ratio of sample, ratio of standard, 0.95 is again here. However, here you see the term here has to times exponential another term here. And the term here, Y is the year of measurement. This is the tau, the term here, mean life. Here we do not use Libby's mean life. We use the best estimate of tau. That means when you calculate delta C14, it has to be very precise. So you use the best estimate of tau instead of Libby's tau. Then this ratio minus 1 times 1,000 would be your big delta C14. For big delta C14, it is possible to have value higher than 0. If you recall your assignment where I asked you to identify the C surface DIC, big delta C14, the value is plus 50 per mil. When you have plus positive value, that means the C14 in your sample is higher than the C14 in your standard. Then this ratio will be higher than 1, and then when you minus 1, it will be positive. You have a lot of C14 in your sample. How can that happen? Because here, as I said, the modern is defined as 1950. That was the year before atomic bomb test. So this standard is not contaminated by atomic bomb. However, your sample, for example, sea surface water, is likely to be contaminated by bomb C14. Therefore, this can happen. Big delta C14 is positive. When you see this, you know your sample is contaminated by bomb C14. Big delta C14 of CO2 in northern hemisphere, and this is year. This is 1950. This is the so-called modern in conventional C14H. At the middle 1950s, the effect of bound C14 start to be visible. C14 value is almost plus 1,000 per mil around 1963, and then decrease over time. The effect of bomb C14 is very obvious and prompt in the atmosphere. If you see this clearly, big delta C14 at 1950, the value is slightly negative, it's not zero. This is the so-called Suez effect. This is caused by fossil fuel combustion because humankind have combusted a lot of fossil fuel, and the fossil fuel carbon has no C14 because these are all very old organic matter. And these old organic matter, which has no C14, enter the atmosphere and dilute the C14 proportion in the atmosphere. Therefore, the C14 at the time is slightly negative. And this graph compares the atmospheric CO2, which is exactly this graph, and seawater. This is surface seawater at mid-ocean drier surface. The type of carbon measured is DIC. It is actually not DIC sample, but from coral. Coral uptake DIC from the seawater to produce their skeleton, and because coral can be well dated, scientists use coral to reconstruct the C14 records back to 1940s. Compared to the atmospheric CO2, the curve was much more smoother, and it has some sort of delay. The peak for the atmosphere is around 1963, but the maximum or the level off is around mid-1970s. So you see a delay in 1 decade. From your assignment, we have asked for surface water DIC. There are 2 carbon sources. One is the bottom subsurface seawater, and the other is atmospheric CO2. And which one will exchange carbon faster with the surface DIC?
The upwelling of the subsurface water is much more shorter, about 1 year.
Very good. DIC is mainly controlled by physical processes. The major controlling factor is mixing with other water. What kind of water will greatly affect DIC? Upwelling. If it's lateral mixing, seawater at the sand layer will have comparable DIC concentration. So even if they mix, you will not see any concentration difference. However, there is a clear vertical gradient. Therefore, if there is upwelling, it will greatly influence the DIC concentration and its isotopic value in the surface DIC. That's the reason why even in the atmosphere we see such a strong spike. In the surface seawater, the signal is much smoother. There is another term that corresponds to big delta C14. This is called absolute fraction modern. F prime is the absolute ratio of samples to standard corrected for the radial decay in the year of measurement. The definition of F, let's review it again. It's defined here. The ratio of standard here is the ratio you measured at the time. It does not take into the account that the standard has also decayed. And big delta C14 already take into account the decay of the standard. Therefore, we can look at the final equation. F prime has a close relationship with big delta C14. That means when you report F prime, you take into account of the decay of the standard. When doing this, you actually use the best estimate of C14 mean life. If F prime is higher than 1, that means you have positive value here, you have bump C14. But usually we will simply report big delta C14 instead of F prime. Go back to this flow chart. We talk about this path here. If you want to go to the direction of very exact data, start from here. Use these 2 normalized ratio to calculate big delta C14, which is this equation. And then you can calculate F prime. Usually we will stop here. We will stop at big delta C14. This kind of very precise value is usually for geochemical studies. For example, when you want to report the atmospheric delta C14, its change over time, you will not use this. People will simply report big delta C14 for atmospheric C14 reconstruction, bomb C14 reconstruction, oceanic C14 reconstruction. Now we go to the last part of data processing, which is for the application of paleo studies. At this moment, we need to be aware that although I have been saying that the C14 production rate today is the same as yesterday or 1,000 years ago or 10,000 years ago, the reality is it is somehow variable in the past. It is not really constant. The reason for that is because magnetic field of the Earth, cosmic ray, when it enters the atmosphere, the Earth has a shield, which is our magnetic field. And the magnetic field's intensity has changed over time. The solar wind also changed over time. If you want to calculate the exact time in the past, you need to do some calibration. And the most famous calibration is so-called tree ring calibration. This cartoon shows you how it is done. This is a tree today. The outermost layer is today. For people who study tree ring, they will have a very special driller, very long, small diameter. So you can just drill like you do it for a cork to open a bottle of wine. You drill it into the middle of the tree, then you can retrieve a tube of wood. From the wood, you will see these rings. The good thing is this material is made of carbon. So on one hand, you can take this tree ring sample, cut them into smaller pieces, send them individually for C14 measurement. Then you will get the C14 data. On the other hand, you can count the ring. I don't know the physiology of tree, but I guess that maybe one ring represents season, maybe, or wet season and a dry season. By counting the ring, you can reconstruct the year for the past. Then you can compare the counted year from the ring and the measured year from C14. You have to assume that your ring is more accurate, because this is something you see by your bare eye, and C14 can be influenced by the variable C14 production rate in the atmosphere. We have to assume that the tree ring is more correct than C14. However, we know that, for example, the oldest tree in Taiwan is probably 5,000 or 6,000 years, but we know the utility of C14 is up to 50,000 years. What can we do? That's what you have to do. For example, this tree is already 5,000 years, so you stop at 5,000 years. In Europe, there are many old houses built of wood. You look for these old houses, maybe one piece of it, and compare the pattern. It is a little bit like the code you use for payment. These codes usually have characteristic patterns, so you can make some correlation. Then you know that, okay, based on the pattern, these correspond to this part. Then you can do some C14 dating. You will know that, okay, this is the younger part, this is the older part. So you can sort of extend your record. This is another building, so you do the same thing and extend. And this is bridge made of wood. You can further extend your records. That's how they do this. That's the product. This is the radiocarbon age, so-called conventional age. This is the so-called calendar age or calendar date. In a paleo lab, they will report in the calendar age, not radiocarbon age. So what's the difference? For radiocarbon age, 0 means modern, right? 1950. However, for calendar date, 0 means 2000. It's the year this figure is published. So you see BCAD. Calendar is a man-made product. This technique is to convert radiocarbon age to calendar date. This is the one-to-one line. This is the actual measurement. This record is built from Irish oak. You see that, as expected, the radiocarbon age and calendar date, they do not fall on the one-to-one line. C14 age is consistently younger than the calendar age. The most reasonable explanation is because the C14 production flux in the past has changed. That's one thing you need to take into account. And the other is the so-called reservoir effect. This is the bottom water DIC. This is the big delta value, so you see the bottom water is already old, from minus 50 per mil to minus 250 per mil, compared to the air. In the case of tree will produce its biomass from atmospheric CO2. So usually terrestrial plant has very little reservoir effect. However, if today you want to date benthic foraminifera, or you want to date coral, you need to take into account that they are benthic organisms and they assimilate their biomass or their test or their skeleton from bottom water DIC, and bottom water DIC is older than the CO2 at the same time. Therefore, when you want to calculate back to calendar date, you need to take reservoir effect into account. This is the corresponding reservoir age. Northeast Pacific is the oldest bottom seawater, and its corresponding C14 age is 2,500 years. However, it is actually modern seawater because you can see it, you can sample it, but its age is 2,500 years. Therefore, when you want to calculate from C14 age to calendar age, which is for climate change, archaeology, and paleo study, you need to do the calibration. And how do you do that? You use an online program called Calib. If you have computer, you can open it and we can play around with it. The Calib C14 calibration program. You can execute online. I really hate its interface. You enter data input menu. This is the place you can play around. We want to enter 10,000 radiocarbon age before present. Standard deviation in age is 55. This can be neglected. This is International Calibration Curve 20. Scientists have built calibration curve for different material. This is IntCalc 20. There is also Marine 20 or Southern Hemisphere Calibration 20, and so on and so on. So there are different kinds of calibration curve. And here, try this one, and then click Enter Data. So the data is entered here. And we can do the same thing for a second one. We choose Marine 20. We use different kinds of calibration curve. For the Marine 20, we have to enter the delta R, which is the reservoir age. So we should give it a reservoir age of 400. And enter again and calibrate. This is the first one, 10,000 plus minus 55. If the calibration data set you use is IntCal 20, this is the age you will get. And the second one is this one with the delta R, which is the reservoir age. Its calibrated age is much younger. So the reservoir age will play a great role in influencing your calibrated age, and also the calibration data sets you choose will also influence. For example, if you choose IntCal 20, the age here is older than the age here. When they report their data, they will actually report probability like this. This is the C14 age, and this is the calibrated age. This is your data probability. This line is the calibration curve with uncertainty, so it's a band. And they will sort of project your C14 age to the calibration curve and then project downwards to the calibration age. Then you will get to know your calibration age with uncertainty. So that's for paleo people who want to use C14 to determine the age.
I just don't understand which one we should use. We know that the calibration age is wrong because it's not the real age. I don't understand when we have the curve with the real age and we have our calibration age that is much younger. What does it tell us how can we interpret it like this? I don't know which one we should use, because you said that calibration age is younger. So is it the true age, or is it, I don't understand which one is the age we should refer to.
This is a true age. This is sort of, you can think of it as a quick and dirty calculation, because the equation is very simple. It's just minus 8,033 natural log f. You haven't done any calibration yet. It's only for a quick comparison. And this has taken into account of the variable C14 flux in the past. It's a very good question because it's an often seen confusion. You might ask, when will I report this and when will I report this? It's very easy. If today you say, oh, the last glacial period ended 15,000 years ago, it is calendar age. If you hear a statement like the bottom seawater in the northeastern Pacific is 2,500 years ago, it's conventional age. Usually, if you want to talk about some records, chronological records, you have to use calendar date. If today you just want to say A is older than B, you use radiocarbon age. Start from next week, we will have 3 weeks of solid Earth. I know this is not a comfortable topic for students at the Department of Oceanography. For A students, please explain the melting behavior of rocks. Rocks melt in a way different from general understanding. There are 2 different behavior. One is called binary eutectic phase diagram, and the other is solid solution phase diagram. These are the 2 figures in the textbook, so you can find the relevant description in the textbook. This is the binary eutectic phase diagram. Please explain if a piece of this rock, which contain this mineral and this mineral, the temperature is going up, how would the rock change? The second is solid solution phase diagram. You see it's very different from this one. You need to explain for a rock containing these 2 minerals, when the rock is getting heated up, what will happen? How would the mineral melt? Then you need to answer this question. Does the mantle cools down or heats up as it melts, and why? Here the examples are all heating up, but the reality is different. So you need to answer the third question. For B student, explain the timing of core mantle segregation using the evidence of hafnium-182, tungsten-182 isotope pairs. This is one of my favorite assignments because I think people who discover this is so smart, creative. You need to read the textbook, the pages here. Then first answer, there are 2 different theories regarding Earth's accretions. You need to first describe what are the 2 theories, and then you need to explain what are the affinity of hafnium and tungsten. To answer this, you need to answer what kind of file they are. Refer to this figure. So this is the figure to answer the affinity of hafnium and tungsten. They are this file, or this file, or this file, or this file. You need to find where is hafnium and tungsten. Third, you need to explain the logic of using these isotope pairs to answer the timing of core mantle segregation. For the last question, you explain this figure.